right. So let's see. So this week, well, any questions first? Maybe from set theory, or we'll touch on some of those concepts again today, right? Especially in the beginning. And like I said, I have some more handouts if you're missing the set theory handouts, but today we're going to be doing combinatorics. And unlike last week, I'll kind of spread it out over the 4 hours, so it's not so hectic. Try to give you time to work through some of those problems. And I have chiseled out some more examples for us to work through and exercises for us to work through together. So hopefully that will be good. All right. So combinatorics is chapter 2 in the textbook. As you may be aware, next Monday is a holiday, so there's no class. Kind of an oversight on my part. That's okay. That's okay. We'll start logic the following week. Luckily, it kind of works out that we have all these Monday holidays anyways. It's fine. We're going to be just fine. Okay? All right. Combinatorics. Fun to say, maybe fun to do. Some people really like it. I'm not one of those people, even though it's kind of part of stats, which is my jam. And so you think, hey, don't you love combinatorics? No, because I find that the questions, the wording is so particular, and it can be really difficult to read a question and figure out what it is you're supposed to do. So I will say this, although some of the assignment questions and some of the exercises that we'll do here are like that, where it's hard to read, and it's probably not until I say, oh, it's this because of this, that you go, oh, okay, yeah, that makes sense. Kind of sell you on it. I do not like to have those on a test, for example. So on a test, trust that it will be very obvious what you're supposed to do, right? It'll be one of a type of question that you've seen before that you know how to tackle, right? And so, because I get that question a lot, where am I supposed to know what to do on a test? No, that's more for when you have time to think about it, and not for under pressure type of questions. Okay, so combinatorics relies a lot on what we call the rule of products. Okay, and so I want to introduce it kind of by way of example. So if you think about this problem, so a snack bar has 5 different sandwiches and 3 different beverages. Now I'm going to be super boring and not name the sandwiches and the beverages. I'm going to call them A, B, C, D, E. How about? That's 5. 1, 2, 3, 4, 5. And the 3 different beverages, let's call them 1, 2, 3. You could use letters there, but it's nice to kind of have a new symbol. Okay. So given that, the question is, how many different lunches can a person order? And so I want you to think about, how would you solve this problem? So I'll give you just a minute to think about it. And there's a couple of different ways, but I want you to also think about what your brain does kind of naturally, and then do it that way. could start by making a tree, right? That's one way to visualize all these different choices and the combinations that you have, right? And so what if I start with the sandwich? I have 1, 2, 3, 4, 5 different sandwiches. You know what? I'm going to make this bigger just because I can. So I have A, B, C, D, E. Now, it's understood that a person is only going to have one sandwich and then they're going to have one beverage. Okay, and so that's unrealistic, but, or maybe it's not unrealistic, but there's a lot missing from the question, right? Where it should say, assume that a person only has one sandwich and they have to have one of these 3 beverages, right? But that's okay. We'll give it a little bit of wiggle room. Yeah. So if I choose sandwich A, then follow up to that, I choose one of 3 beverages, right? 1, 2, 3. And I can do that regardless of which sandwich I chose. I'm always going to have 3 beverage options. So now, each of these branches represents a different combination of sandwich and beverage, right? In fact, it represents, so if we write out the combinations at the bottom here, we would have all the different sandwich beverage matchups that we could have, right? And so we could have A1, A2, A3, B1, B2, B3, C1, C2, C3, D1, D2, D3, and E1, E2, E3. Then you can count all these different combinations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we get 15 different lunches. That's pretty good. This isn't always convenient to write out, let's say there are 20 sandwiches and 13 drink options. Uh-oh. Imagine your tree just went. But what happened here? We had 5 sandwiches, right? So 5 branches, and each of those were followed by 3. So really what we're using is the rule of products. So the rule of products says that, okay, I have to choose a sandwich and I have to choose a beverage. I have 5 choices for the sandwich and I have 3 choices for the beverage. If I multiply those, I get 15. You can read this multiplication as and, right? If you find yourself saying, okay, you are going to have one of 5 sandwiches and one of 3 beverages, right? Or you have 5 choices for the sandwich and 3 choices for the beverage, then that's where the product comes in. So what you're going to find is that I use this, I call them slots, right? And so usually underneath I'll write kind of what it is that I'm looking at, right? What am I trying to pick from? And then how many options do I have for that slot? Okay. And so this is what we call the rule of products. Okay. we've already seen the rule of products, sort of, when we said last week that the cardinality of the Cartesian product of A and B, back to haunt us, right? All things that you're expected to have a good handle on now, right? From last week. And so let's take it nice and slow. So the cardinality are the vertical bars, and then A times B is the Cartesian product of A and B, because A and B are understood to be sets. Right? But what we said last week was that, okay, the cardinality of the Cartesian product is just the product of the cardinality of each of the individual sets, right? And so we've got a little reminder here. If we let A, B, C, D, E looks familiar, right? Just like the sandwiches. It's more fun when you call them sandwiches though. And B be the set 1, 2, 3 beverages, maybe, right? And so then if we list the elements in the Cartesian products, right, we get A1, A2, A3. That looks like A1, A2, A3, B1, B2, B3, and so on and so forth, right? And so notice here that this, I'll just say, looks similar. Just so you kind of make a note of that. So you first have to choose a sandwich and then you choose a beverage, right? But inside, nope, scratch that. Just fact. First you have to choose a sandwich, then you choose a beverage. Okay. The cardinality of A, I needed more room. I was trying to keep it nice and slim, but came at a cost. The cardinality of A is 5, right? And the cardinality of B is 3. Remember, the cardinality is the number of elements in the set. And so then by this rule, right, the cardinality of the Cartesian product of A and B must be 5 times 3, which is 15, which is exactly what we found with our tree, but also those look exactly the same as this set here. Yeah. So I do expect you to remember that this times is the Cartesian product. And of course, the cardinality is the number of elements. Okay. So the rule of products, we're going to start with just 2 things, but then we'll quickly extend it to any number of things with some caveats. So if 2 operations must be performed, and if the first operation can always, and I'll highlight the always, be performed P1 different ways, and the second operation can always be performed P2 different ways, right? There are always 5 sandwiches and there are always 3 beverages. Then there are P1 times P2 different ways that the 2 operations can be performed. One thing to note, this only works if P2 does not depend on the option that's chosen in the first operation. For example, if you get sandwich B, maybe you have to have beverage 1, right? And so then that would alter the number of options that you have depending on the sandwich that you chose. And so what we're really saying is that P2 has to be independent of P1, right? It can't depend on what your first choice was. We will have ways of solving problems like this, right? So that's okay, but we'll get there. And so, of course, we can extend the rule of products to sequences beyond 2 operations. And so if we have n operations, right? So let's think about first grab a sandwich, and then you grab a beverage, and then there's a dessert, right? And then there's, I don't know, Happy Meal prize, I don't know, whatever. Right, so now you have n operations. So what you can do is you can just multiply these as long as they're all independent of each other. So kind of the standard example is multiple choice questions. You've got a multiple choice exam, right? We don't, but let's imagine that you do. So a questionnaire contains 4 questions. I'll just highlight the information that we need here that have 2 possible answers, and then 3 questions with 5 possible answers. Or I guess 2 possible and 3 questions with 5 possible answers. Yeah. I really should have given myself more space here. That's okay. It is on here, but I find it's better if I write it out. So what's this going to look like? Right. First, you have 2 possible answers for 4 questions, which means that if you did your slots, right, let's do them, I don't know, down here. 1, 2, 3, 4. And then you have 3 questions, 1, 2, 3. Or maybe I'll use a different color here. Let's use green. 1, 2, 3. So if there are 2 possible answers, then the answer you gave in question 1 is not going to change what you give in question 2, right? Or you're not going to let it determine what answer you give in the next question. And so for each of these, you have 2 possible answers to choose from. And then for the next 3 questions, you have 5 possible answers. So now you've got one of 5 to choose from, which means that there are 2 to the power of 4 times 5 to the power of 3, or if you just want to multiply them out, that's totally fine too. So there are 2,000 different ways to answer that questionnaire. And there's only really, what, 7 questions, right? And so when I was in grad school, I was TAing for my supervisor, and he had 2 versions of a test, and people didn't know that. And so he calculated and published a paper on the probability that you would answer the same way that your neighbor did, which was correct on that version, but very wrong on your version. And the probability is very, very small. Obviously, it was like 30 multiple choice questions, 4 questions each. What would that be? 4 to the power of 30 options. Probability of just choosing something just randomly is very, very small. So that was mean of them, I think. 2 versions. I do that too, but I let you know in advance. So 2,000 different ways. that we can answer this questionnaire. Any questions so far? So that's a reasonable type of question where there's not, you know, a lot of, there are no assumptions missing here, right? That's what I'm looking for a test question. And so kind of an easy question on a test would be, all right, so you're writing in a multiple choice exam and there are, you know, 3 questions with 5 options followed by 14 questions with 2 options, and then how many possible tests or answer combinations are there, right? And so you use the rule of products, you're good to go. Right? So the power set, we talked about the power set last day. Power set was what? Power set was the set of all possible subsets of a set A, for example. Right? And so then if we have to list all the possible subsets, then one thing that might be good to know is the cardinality of all the possible subsets, which means what? It means I'm looking for, or I know how many subsets I'm looking for, right? The cardinality of the power set of A is how many things, how many elements are in my subsets, or how many subsets do I have? And just as a fact, it's a theorem. It's going to be 2 to the power of the cardinality of A. And so the proof is super brief. So I have it on here. What are we going to do? We're going to see a few proofs today, just to get us warmed up for logic, which is in the next chapter, where we have to do proofs. And so let's see, how would we approach this proof? So what we're going to do is we're going to think about some B that's an element of the power set of A, where the cardinality of A is n. So A has n elements, is what that's saying, right? For each element x in A, then there are 2 choices. Either x is in B, right? So x is in that subset, right, which is part of the power set, or x is not in B, right? Only two choices. And then what we have, so because there are n elements, right, we do that for each of the elements. And so we have 2 times 2 times 2 times 2 times 2 for each of the n factors or elements, I'll say. Factors or elements. Which is 2 to the power of n, right? And then n, remember, was the cardinality of A. And so there, it's proven. That seems pretty simple. I will say that in the textbook, if you're reading the textbook, for some reason or somehow, they forgot the cardinality, the vertical bars. So but I spent enough time staring at it that I feel confident correcting them. Will I submit something? No, probably not. I'm assuming everyone else is catching it too. Bystander. So that's kind of a fun one, right? Because what can I ask you now? Going back, so this would be kind of tying together set theory and combinatorics. right? Because what kind of a question could I ask here? I could ask, let A be the set of A, B, C. Let's stop there. Yeah. Find the cardinality of the power set of A. Right? Or in words, how many possible subsets are there? Or how many possible subsets are there of A? All you need to know, right, then you could list all the possible subsets of A, right? But that's going to get really, really annoying once you hit kind of 4 or 5 elements. Even at 4, it gets really kind of annoying. And so now that's where the benefit of knowing this theorem comes in, because then you can say, okay, well, I know that the cardinality of the power set of A is 2 to the power of the cardinality of A, which in this case is 2 to the 3, which is what? 8. 8 possible subsets. That's nice to know how many possible subsets there are. Even if you have to list them, right? A nice place to start is knowing how many you're looking for, and then you can kind of work at it. Yeah. Yes, but that would be taken into account here, because all of these could be not in it, making it. But yeah. So it is, so the empty set is an element in the power set. Very good. All right. So what I've done, kind of after each section, I'm not kind of labeling them sections, but they are. So we're gonna do, I've chosen kind of one of medium to hard difficulty for us to go through together, and then I'll give you some time to work through these other questions, and then when I post the notes, we've got the solutions there as well. Okay? Because I don't know what the timing is going to be like, I'll hold off on going through those solutions until the end of class. If there's time, then we will. But I'm just figuring out the timing still. All right. So I will give you a moment to try the exercise, and then we can go through it together. you may or may not find using 8 slots useful, right? And putting the number of options in each slot and then multiplying through. Maybe. Let's start with the first one. So we've got 0s and 1s, so we have 2 options, obviously. And so for each of these, and like I said, you might find the slots helpful. I definitely do, especially when I'm trying to kind of figure out what's going on. And so I've got 8 bits and two options for each bit. So no restrictions on this one, right? It's just going to be 2, 2, 2, 2. And if I multiply all these, so when you've got the slots, you can just multiply through. You get 2 to the power of 8. So you have 256 options. Fair enough. We can add restrictions. Right? I guess this one assumes you know what, bless you, what a palindrome is. Same backwards as forwards, it does say, but still. What can you do? There are a couple of ways that you can do it. I would say, okay, if I have to have 4 and then the same 4 replicated, right? Then I can allow for 2, 2, 2 options here for the first 4, right? And so here I can have any 2 numbers, or so any digit, right? But then I only have one option, one option, one option, one option, right? Because this one has to be the same as this one. This one has to be the same as this one, right? And so now I've kind of forced these to be the same. So I only have one option. So these must be the same as the other, or as the first. I'll say backwards, I guess. Right? Because this one has to be the same as this one. This one has to be the same as this one. This one has to be the same as this one. And this one has to be the same as this one. Then it's a palindrome. Which means that I have 2 times 2 times 2 times 1 times 1 times 1 times 1, which we can ignore. So 2 to the power of 4, which means I have 16 different palindromes. pretty boring when it's binary, but still. You could extend this, right? How many letters are there in the alphabet? There's 26. And so now we tend to ignore words that make sense and words that don't make sense, right? But you could do the same thing. How many 8-letter words are palindromes, right? Ignoring words. How many 8-letter things are palindromes, right? How many of those are there? So then you could extend this and say 26 times 26 times 26 times 26, but then 1, 1, 1, 1, 1, because I have to force it to be the same as the previous. Okay. This one's sneaky. How many different bit patterns have an even number of ones? What would you do here? If I tell you, okay, up until here, you have 2 choices, right? As long as you force this one to correct whatever's happened previously, you can force it to be an even number of ones, right? By letting this be 0 or 1, right? And so what happens is you have 2 choices, 2 choices, 2, 2, 2, 2, 2, but then you force this to be 1, right? Because if you get to this point and so far you have 0 ones, you only have the choice of making this a 0, right? Which means you only have 1 option, right? What if you get to this point and you only have 1 1? Then you'll only have 1 choice. If you're forced to make it even number of ones, you have to make it a 1, right? And so in each scenario, you only have 1 choice for the digit there. Kind of confusing because we are talking about 0 and 1s as well, but here, so this has to be 1, since we would have no choice for the last digit, or I guess last bit, call it bit, binary digit. Which means that you would have 2 to the power of 7, which is 128. Okay. I want to give you, I don't know how long. Let's say 15 minutes to work through these problems. I'll pause the recording because that would be a lot of dead air. But yeah, let's go to 5-2. All right. So I forgot to mention one thing. So if you're using the PDF that I posted on Moodle, I see just one here, but then it's missing parts A and B, so I'm gonna re-upload it. But just so you know, there was no follow-up question, so I caught that, but forgot to post it on Moodle. But just itty bitty. Okay, so I'll just do a quick run through. You've spent time working on it. For your shirts, got 4 options for the size, 6 options for the color, and 3 options for the pocket, making 72 different combinations. Okay. How I solved the pi mu epsilon seating arrangement one is I pick away, so I start in row 1, and because I'm multiplying, it doesn't really matter where I start, right? Because 6 times 5 times 4 times 3 times 2 times 1 is the same as 1 times 2 times 3 times 4 times 5 times 6, right? And any kind of mashup of that, right? And so, but what I want to think about, or I want you to think about, is if I start here in, let's say, row 1, I have 6 people to choose from first, right? But then that person has been placed, right? One of the 6 doesn't matter, but I have 6 choices. So now I only have 5. And then I have 4, 3, 2, 1. Yeah. Yeah, so the 6 and the 5, and so all these numbers are open to any of the 6, right? And so this is how you would figure out all the different ways that you could arrange 6 people. Okay. But because one person's already seated, and it doesn't matter, it's one of those 6, right? So here, the first person has been seated now, right? Now I only have 5 people to choose from, but I can choose from all 5. Then I have 4, and then 3, 2, 1. And kind of getting ahead of myself here, but this is what we call 6 factorial. Now, we haven't seen factorial until the next page, I want to say. But you have probably seen it at some point. Really 6 factorial. But 6 factorial is just 6 times 4 times 6 times 5 times 4 times 3 times 2 times 1. Okay? And a lot of calculator buttons have the factorial button that you can use. Okay? But we'll talk about factorial in a bit here. A license plate problem, kind of a go-to test question, right? Some criteria, and so how many alphanumeric slots do we have? So in this case, we have 3 digits followed by 3 letters, but the first digit is never 0, right? And so we can choose from, so in general, for our digits, we have 0, 1, 2, 3, 4, 5, 6, all the way up to 9, right? Meaning we have 10 choices just in general. But because the first digit cannot be 0, that's the rule, I guess, in this case. And so then I only have 9 things to choose from here, right, for this first slot. But then the next 2 are allowed to be 0, right? Anything 0 through 9. So then I have 10 options again. And then I have letters, 3 letters, and there are 26 letters. And there's nothing about repetition or anything like that, which we could kind of level up with if we wanted to. But for now, we're just assuming that repetition is allowed because they didn't say. Which means that there are a lot of plates that we could generate, and now you can figure out how many we can generate with our new, what is it? Alpha numeric alpha license plates. I've got a thing for license plates. I don't know what it is, but anyways, I always pay attention to license plates. Another reasonable test question, right? If I give you A, 1, 2, 3, 4, then how many different subsets of A are there? So notice I'm not asking you to list the subsets, just tell me how many there are, right? That relies on you knowing this theorem, right? The cardinality of the power set of A is 2 to the power of the cardinality of A. That's a good one. Okay. And so the cardinality of A is 4, 1, 2, 3, 4 elements. And so there are 16 different subsets. Here, this one's sneaky, like I announced, because proper subset is just not A itself. So the empty set is a proper subset, and all the other subsets except for 1, 2, 3, 4, 5 in this case. Notice that there's a new number here of elements. So now the cardinality of A is 5. That's a good kind of part A of a question given this set. All right, what's the cardinality of A? How many subsets are there? Right, there are 32 subsets. So in the power set, but that includes the improper subset, which we remove. So now there are 31 proper subsets of A. Yeah. Okay. Now, there are probably lots of ways that you could approach this problem, right? But the key is, okay, so if you've got A, B, and C people, and they're supposed to be seated in a row of 3 chairs, A and B are identical twins. So what we're supposed to take from that is that a total stranger is not going to be able to tell them apart. Okay, and so how many seating arrangements of these persons can there be? And of course, hopefully, if you're A and B's mother, then you can tell them apart. And so then they would be distinct elements, right? And so the easiest way to tackle this, I think, because there are only 3 options, right, then I can easily list all 6 of the arrangements. All right. I'm going to start with what mom sees, just because then they're distinct. And then what I can do is say, okay, if A and B are identical, then wherever I see a B, I can just replace it with an A, right? And so to a stranger, what I've done is I've just replaced all the B's with A's because they look the same. Right? Then I remove all the duplicates. I have AAC. Well, that's a duplicate with AAC. Right? ACA is a duplicate with ACA. CAA, CAA. So there are 3 unique arrangements. Right? These are kind of fun, right? How many different meals can you make? Right? And so you've got a choice of fish, lamb, or beef. So 3 options. A choice of peas or carrots for a vegetable, so 2 options, and then a choice of pie, cake, or ice cream for dessert, which means you have 3 options, making a total of 18 different meals. Everyone's going to get that type of question, right? How many should I put on the test? 1, 2. Those ones are pretty fun. 5. So this is the one, if you download it on Moodle, I'll update it, but it was missing this parts A and B, meaning there was no real question. But if a questionnaire contains 6 questions, each having yes, no answers, and then for each yes response, there's a follow-up question with 4 possible responses. Now, what we want to do is we want to map out all the total responses for each question, right? So first thing we're going to do is we're going to draw a tree diagram to show how many ways a single question in the questionnaire can be answered. So this is for each question, we can have either a no or a yes as my answer, right? If my no, then the overall answer is just no, right? There were no follow-up questions, nothing like that. However, if I have a yes, then there was a 4-question follow-up, right? 4 possible responses, which I'm going to denote by yes 1, yes 2, yes 3, yes 4, just to indicate that they're all different yeses. So now the possible outcomes, so each question has 5 possible outcomes. It can be no, right? That's the end of the road. Or it can be yes 1, or yes 2, yes 3, or yes 4. And so then I have 5 possible outcomes, which we can then use to figure out how many ways can the questionnaire be answered. 5 times 5 times 5 times 5, blah, 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 6 times 5 to the power of 6, 15,625 different ways. That's a lot. No, I'm easy. If you do this, I want to see it condensed somehow. But if you're choosing between 5 to the 6 or 15,625, they're the same to me. So I'm good with either are. Technically, I could be convinced that this is also the answer. It's just not worked out nicely. Not a full answer. So, but either one of these is totally fine. Okay. I think that was. Any questions about those? Nice. If you didn't have time to work through all of them, you can go back and work on them. But I guess I've spoiled it now. Nah, you won't remember. Okay. We're going to talk about a specific case called permutations. And so what we want to have in permutations is if there's some specific order. Okay? And so let's do an example. So how many different ways can we order the 3 different elements of the set A, B, C? And so now this is kind of similar to the sandwiches and the beverage problem, except now if you've used the letter, you can't repeat it. Yeah? And so here, the 3 different elements means no repetition. So we're eliminating those options of A, for example, which means we could have something that looks like this. So for my first letter, I have a choice between A, B, or C. If I chose A, and I definitely should have given myself more space here, A, then, oops, sorry. I only have 2 options. I went overboard. I have 2 options. I can choose B or C next. And I'm just going to move this over here. So then I can have B or C. If I chose B first, then I can have A or C. If I chose C first, I can have A or B. If I've already used A and B, next one has to be C. If I've already used, now how you read this is going to go A and C, then the missing one must be B. B, A, C, B, C, A, C, A, B, C, B, A. I can list all these: A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Let's see if I can shrink this down. Okay, not really. I'll put it there. Not very nice, is it? at first, I have 3 choices, right? But at the end of each of these branches, I only have 2 choices. And then at the end of each of those branches, I only have 1 choice, right? And so we could also do it this way, 1, 2, 3. Right? Just thinking about how many ways I can order these things. For the first one, for the first letter, I have 3 options. Right? If I've used that letter, I can't use it again, which means I have 2 options. Now, I've used 2 out of the 3, ain't bad. So now I only have 1 option left. This is a little bit easier way to get to 6 than enumerating all the possible options, right? This has the benefit, again, of seeing all the possible options and what they are, right? But if we're just going for the number, then I'd say that this is maybe the easier way to get there, right? 3 times 2 times 1 is 6. So, okay. A student's taking 5 courses in the fall semester. Do they make you take 5? Or are you one of those 7? I know some engineering, they do 7. Just work them to the bone. 5 is reasonable, I think. A student's taking 5 courses in the fall semester. How many different ways can the 5 courses be listed? Course 1, 2, 3, 4, 5. First, I have 5 to choose from. Then I have 4, 3, 2, 1. 120. We already did this, right, without calling them permutations, right? Earlier when we had the 6 factorial, right? But now we're seeing it kind of, okay, no repetition, then it's going to look like this, right? Kind of decreasing as we go through. So in these rules of products, we're asked to order or arrange elements from a single set. Okay, that's first part. That's always true. And then if each element is listed exactly once in each list, then we have a permutation. There are n choices for position 1, and there's n minus 1 choices for position 2, and n minus 2 choices for position 3, and so on and so forth. Just to give you an example, now I'm not going to make you write anything down for this because it's just going to talk you through how factorials came about, because here we don't really see a need for shorthand, right? 5 times 4 times 3 times 2 times 1 is relatively simple to communicate, okay? But if we have a scenario like this, so we have a baseball team, then if we talk about the alphabetical ordering of the players, then that's 1 permutation of the set of players, right? Each player is only listed once, and so there's no repetition. And so there are lots of other orderings that we could make up. In fact, some of them you could just assign a random number and then sort by that. That's also a permutation. You could sort by batting average, age, or height, or any other kind of key. Okay, so that's called a key. That's not important, but that's wanted to mention it so it doesn't come up. Each key is going to give a different permutation of the names, right? So it could be, like I said, just a set of random numbers applied to each of the players, and then that's the key, right? And so it doesn't have to be something reasonable all the time.
But if there are 25 players, then there are 25 times 24 times 23, blah, 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 times 1 different permutations of the players. Okay? That's a lot. Okay? In fact, it's whatever this number is. And I don't want to work with that. Looks terrible. Okay? And so we need a more compact way of writing these things, right? And so that's where the factorial comes in. So if we have n is a positive integer, and so then n factorial is the product of the first n positive integers and is denoted by n factorial. So we joke in our office that's really n exclamation mark. Really n. Now, as a fact, 0 factorial is 1. We're going to use that, so that's why I want to highlight that there. We have to find the factorial of n of 0 through 7, right? We can set up a table like this, where maybe I have n followed by n factorial down below, and we're going to start at 0, 1, 2, 3, 4, 5, 6, 7. I'll scoot this over. On your calculator, probably have a factorial button. Can I find mine? Feel like I have seen it. But where is it? Maybe I don't have one on this one. That's okay. Do you guys have one on yours? Maybe not. Oh, there it is. Found it. Okay. On my calculator, I guess we'll do this. Oh boy. This again. I found it here. Really X. That's hard to see, but it's on there. So you can use your calculator if you want. Let's try 7 factorial. Let's start there. 5,040. Or you can do it kind of longhand. 7 times 6 times 5 times 3 times, no, 4 times 3 times 2 times 1. But no, thank you. I'll work my way backwards here. 720, 120, 24, 6, 2, 1, and 1. You can use the x factorial function on your calculator. That might be good to know. How about a factorial fact? Usually I have little fun facts, LFFs, but here's a factorial fact. If the cardinality of A is n, and there are n elements in A, right, then there are n factorial ways of permuting all n elements of A. Okay. First slot, you have n options, then you have n minus 1 options, then you have n minus 2 options, all the way until you have only 1 option left. right? And so there are n factorial ways to permute all elements of A. That's not usually what we want to do. We want to have just a small set from a larger set of elements. And so a more general situation where we want to permute k elements out of a set of n objects where k has to be less than or equal to n. For example, a club of 25 members will hold an election for president, secretary, and treasurer. Now, because we have, so in this order, so because I have these distinct positions, right, whoever becomes president will also can't be secretary and treasurer or treasurer, right, but also these are distinct positions, right? And so assume a person can only hold one position. How many ways are there of choosing these three officers? Now, for me, I like my slots. You might be ready for the permutation counting formula, but if I have the president and then I have the secretary and then I have the treasurer, 25 members, one of those has to be president. I have 25 options. Now, whoever was chosen president of those is out of the running for secretary, but I have 24 to choose from still, and I have 23 by that same logic for the treasurer, right? Decreasing by one as I go. So now I can multiply this out and find, oops, not too many zeros. There are 13,800 ways that we could have choose a president, secretary, and treasurer. Okay. So a permutation, I'll highlight this whole thing here. So we're going to come back to it, but an ordered arrangement of k elements, right? President, secretary, treasurer, that's an ordered arrangement. Okay. Selected from a set of n elements where k is between 0 and n. There are no two elements, the arrangement that are the same. It's called a permutation of n objects taken k at a time. And so what we use to denote that is this PNK. And there's usually an NPR button. Mine looks like NPR on your calculator. Which is the same thing as PNR, using R instead of K, but that's okay. Huh? Okay. PNK, we know, is going to be n times n minus 1 times n minus 2, all the way up to n minus k plus 1, right? And then we stop, because here I have n things to choose from, right? But I want to choose k elements. We're going to prove it. So let's see here. So how about we just accept it as fact, and I'll do the proof with you guys. But how we can summarize this is, do you remember the product notation from last day? We had this product notation, so a capital pi is the product. From j equals 0 to k minus 1. So because j starts at 0, it goes to k minus 1, not 1 to k. But you can have n minus j, the product of n minus j is the same thing as saying n minus 0 times n minus 1 times n minus 2 all the way up to n minus k minus 1, right? Which is n minus k plus 1 if you dissolve the brackets. This becomes n factorial divided by n minus k factorial. We're just going to use that, right, for now. And we'll simplify it. We'll do some work simplifying it in a bit. I'm going to add a page for our proof here. I don't need this, but I do need this. Proof of the permutation counting formula. We're going to split these into two cases. So the first case is if we just have k is all the elements is equal to n. So if k is equal to n, then what does that look like? If I'm trying to permute k out of n elements, but I'm letting k be n, that's going to look like this: 1, 2, 3, 4, all the way up to here, right? N times n minus 1 times n minus 2. Shouldn't have done so many. N minus 3 all the way up to 1, which is n factorial. That's the special case if k is equal to n. Which means that therefore Pnn is n factorial we can check to make sure that that's the same as n factorial, or maybe I'll write it two separate lines here. N factorial over n minus n factorial. Okay. This part, we said, okay, we can go from here to here just as a rule because it was given to us here. So Pnk, I can translate, but I want to see that it actually does equal n factorial, and then I'll be convinced, and you will be convinced as well, right? N factorial over n minus n, which is 0 factorial, but 0 factorial is 1. So this does, in fact, equal n factorial. Yeah. So far, so good. What about all the other values of k, all the other possibilities for k? What's that going to look like? So case 2 is if k is between 0 and n, not including n, but it can be 0. Okay. Then we have k positions to fill with n elements. We have k positions to fill with n elements. So what we can do is we can say, okay, position 1, which is the same as position 1, 2, 3, 4, 5, blah, 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 blah. But it's really hard to visualize at ending at some unknown k, right? And so I'm not gonna do this, I'm just gonna list them out. Okay. So position 1 can be filled by n minus 0, which is n elements. Position 2 can be filled by n minus 1 elements. Position 3, we'll do one more, n minus 2 elements. Oops, we don't need 2 dots. What's the pattern here? 3 minus 1, right? N minus 3 minus 1, n minus 2 minus 1, n minus 1 minus 1. And so for k, we have n minus k minus 1, which is n minus k plus 1 elements. So I can multiply these things through, and I can say what color scheme. Kind of went a little rogue here on the colors, but that's okay. P of nk is going to be n times n minus 1 times n minus 2, all the way up to n minus k plus 1, ending at some unknown k. Okay. How can I summarize this as n factorial over n minus k factorial? A little bit of a leap, sort of, I guess. But what we can do is we can rewrite this as n times n minus 1 times n minus 2, all the way up to n minus k plus 1 times n minus k factorial as n factorial, divided by n minus k factorial. I can expand this n factorial, and it's going to be a trick that we use quite a bit, is we expand one of these factorials until we hit the other one, and then we just finish it off with n minus k factorial, right? And then that just carries out the rest. Because what can I do now? I can cancel this n minus k factorial with n minus k factorial, and all of a sudden, I'm left with this product that I was trying to summarize. And so that's why this is the summary of the number of permutations from n elements of k. So this trick is very useful, right? So if you have n factorial, so just as a quick example, you have n factorial divided by n minus 2 factorial. You can simplify this and rewrite n factorial as n times n minus 1 times n minus 2 factorial, right? The n minus 2 factorial keeps going. So this is n times n minus 1 times n minus 2 factorial over n minus 2 factorial. But these guys cancel each other, and all I'm left with is n times n minus 1. That's neat. So we'll use that property, that expansion, quite a bit. Okay. Nice. I should have put some sort of box around this. It's kind of important. What if a club, just as an example, has 8 members eligible to serve as president, vice president, and treasurer? Same kind of scenario. How many ways are there of choosing these officers? There are 2 ways you can solve this. You'll get the same answer. Really? My go-to is whenever I can, I use my slots. Don't have to, but I do. So the first way, right, I have 8 members who are eligible, and so the first one is chosen as president, then I have a vice president, and then I have a treasurer, meaning there are 336 different ways that I can choose these positions. Or if you prefer, the same thing would be to say, how many ways can I permute out of 8 things, 3 elements? So P8-3 or 8P3 on your calculator. But what you should find is that it's 336. You've got your calculator, and so hopefully you can make sure 8 NPR3, I get 336. But what else could you do? You could use the formula. You could use the formula for NPK. NPK, or PNK, I guess, is n factorial over n minus k factorial. So I have so this would be 8 factorial divided by n minus 3. So 8 minus 3, 5 factorial, which is 8 times 7 times 6 times 5 factorial divided by 5 factorial using that same expansion technique, but then I'm just left at 8 times 7 times 6. Right? So no matter which way you slice it and dice it, you're going to get the same answer. The hardest thing for me, I think, is recognizing that I need the P function, right? The permutation function, because we're going to introduce the choose function. And so I like just using the slots and not worrying about it, but it's up to you. How about another example? If I have the digits 1, 2, 3, 4, 5, how many 3-digit numbers can be formed if no repetition of digits can occur? Well, 3 digits, 1, 2, 3. I have 5 things to choose from, so 5, but then no repetition, 5, 4, 3, 5 times 4 times 3 is 60. Or if you prefer, P of 5, 4, or sorry, 5, 3, which should also be 60. How many 3-digit numbers can be formed if repetition of digits is allowed? Okay. So now we're back to 1, 2, 3 digits. I've got 5, and then I have 5 again, and then I have 5 again, because they're allowed to all be the same. All right, and so now I have 125 options. level up here. How many 3-digit numbers can be formed if only non-consecutive repetition of digits is allowed, or are allowed, I guess? Can still use my trusty slots. First digit, I have 5 choices, right? I can pick any number. There's no repetition yet. And so I've got 5. For this next digit, I can't be whatever number I chose here, right? So I only have 4 things to choose from. What the last one? Again, I'm allowed to be the same as the first digit, right? I'm just not allowed to repeat whatever I had here. So again, I have 4 to choose from here, but it's not the same 4 as I had in the second slot, right? Because this one's back in play, whatever the first digit was is back in play, and the second one's out. That one's a little bit of a thinker, I think. That's pretty reasonable. But we're just learning it, so it doesn't seem reasonable now, but you'll look back and think, yeah, it's pretty reasonable. How about these? So again, with the 3-digit numbers, how many 3-digit numbers? So consider the 3-digit numbers that can be formed from the digits 1, 2, 3, 4, and 5 with no repetition of digits allowed. Okay. How many of these are even numbers? Okay. What if we start here, 1, 2, 3 digits? First, we have to think about what it means to be even. Now, as long as it ends in an even value, right, then it's even, right? And so what are my options? 1's not even, 2's even, no, 4 is, 5 isn't, right? And so here, I'm gonna say this, start here. So this must be 2 or 4, right? From these guys, right? We're not just talking about any numbers, just the numbers 1, 2, 3, 4, 5, right? That might be confusing. So it must be 2 or 4, which means I have 2 options here. 2 out of the 5. Then I have 1, 2, 3, 4, 5 options, but I only have 4 to choose from here, right? Because I've already used 1, and repetition is not allowed. Right. Is not allowed. Which means that by the time I get to here, right, I only have 3 things to choose from. Notice that because we're multiplying, right, you could have thought about, so you could have dealt with this to the last digit to make it even, and then gone here and said, okay, then I only have 4 to choose from because I used one of the even digits as my last number. right? And then I have only 3 to choose from, but 3 times 4 is the same as 4 times 3, so it doesn't really matter. So I have 24 even numbers. For this next one, I would, yeah. It makes it easier if you break it up. So, how many are greater than 250? There's a couple of ifs here, right? And so, okay, 250, let's start with this first one here. It can be 2, 3, 4, or 5, right? So here, this one can be 2, 3, 4, or 5, right? So what it means is this number that we're spelling out has to be greater than 250. Now this next one, this is where it makes more sense to split these guys up, right? Because if the first one is 2, then the second one has to be 5, right? So then, if first is 2, it must be 5. If first is 3, 4, or 5, it can be any value. Okay. Same idea here for this last one. If, oh, we're not doing 1 first because it's out of the running. If 2 is first, I have how many options to make it greater than 250? So here's a 2, but if the first one is 2, this one has to be 5, and which means that I have 1, 2, 3, 4, 5 to choose from, but no repetition, right? So the 2 and the 5 are out, leaving me with only 1, 3, or 4 to choose from. Right? It can be 1, 3, or 4. So I have 3 choices there. If 3 is first, then it can be any number here, right? So I've used up, again, I've used up 3 and one of these other 4 numbers, leaving me only with 3 options, right? Doesn't matter which 3, that's all we need. So 3 options. If the 4 is first, then we still have 3 options, right? Because as long as it was 3, 4, or 5 first, then it can be anything, right? So then I have 3 options, and 5 first, then I again have 3 options. Now where can I'm gonna add a page here. So like I said, I think the easiest thing to do is to just list them out when we meet downstairs for part 2, because pretty sure I'm out of time. So we'll pick it up here downstairs. See you then.